Good morning, everyone. Thanks for coming to my talk. So I'm going to talk about a problem related to unsupervised learning, and this is about community detection. So in particular, I want to find strong communities from cooperative games. So it's a game theoretic perspective. So this work is joint work with Ali, Henderson, and also my student, Chung. Okay. So first, let me motivate the problem. So there are many community detection algorithms out there, but then they have some limitations that we should address. So what are they? Well, first let me explain what is community detection, or another word for that, which is shorter, is clustering. Okay. So what is clustering? So that's just a basic principle in unsupervised learning. So we want to group similar things together while separating the similar things apart. So this is perhaps the first things you would do when you interact with an environment. So this basic principle or basic concept is very important, and it has applications in many areas. So what are they? Well, I'm going to talk about some basic methods for clustering. So one of them is conditional clustering, the other is hierarchical clustering, and finally graphical clustering. And there are many more. I'm only going to focus on 3 of them. Okay. So to explain this concept, let's consider an example. So suppose I have 4 pieces of data, 1, 2, 3, and 4, and I only have 2 attributes, so set1 and set2. So what is the problem of clustering? So for partitional clustering, we ask which partition is the best in separating the similar things and grouping similar things together. So anyone know? Well, if you plot the graph of these 4 points, it will be clear to you. So you should group 1 and 2 together and 3 and 4 together, right? Because they are closer to each other. Well, the clustering solution we are looking for is 2 sets. The cluster C1 that connects to 2 element 1 and 2. Another cluster C2 that connects another 2 elements, 3 and 4. Okay. Another way to write the answer is to use the cluster label. So this is the cluster label. The label for 1 and 2 are the same, and they are equal to 1, the first cluster. The other one is C3 and C4. The label should be 2 because they belong to the second cluster. Okay, so that's it. So this is about partitional clustering. But what's the problem of this? Well, if you have many more attributes, then it is difficult to plot this graph. So it is a very high dimensional graph. So we need mathematical criteria to look for the clusters. And also a fundamental problem in partitional clustering is, how do you know there are 2 clusters to begin with? Okay, so this is difficult. So a suggestion is, a solution is using hierarchical method. So what is hierarchical method? So the idea is, for example, group the points together when they are close enough. So suppose if we consider a distance threshold of D1, then we will be grouping 1 and 2 together and 3 and 4 together because they are within reach by a distance of D1. Okay. Now we will further raise the threshold to D2, then everyone will be connected and they will be grouped into a single cluster. The right-hand side, this tree diagram basically describes the entire hierarchy of clusters, and it is called a dendrogram. So dendro means tree-like. So it is a diagram that probably many of you already know. Okay. But then, if you look at this solution, basically you are looking at the pairwise distance between the points. So this is actually can be turned into a graph clustering problem. You can abstract all the details by using a graph. So this motivates the other field of work, the graph clustering problem. So what is graph clustering problem? So we start with, let's say, a weighted graph, undirected here. And this can be described mathematically using an adjacency matrix. So this is, I think, very, very clear to all of you. So how should we group nodes into clusters? So it is obvious that we should put 1 and 2 together because they are related by an edge. Okay? So partition method should give you this result. And what about hierarchical solution? Well, of course, for hierarchical solution, we should also group 1 and 2 together. We can also give a similarity rate threshold to say that 1 and 2 will combine into a cluster at a similarity of 1. But then hierarchical cluster will further continue and raise the and reduce the similarity threshold to 0, and then in that case, all the nodes will be grouped into one single cluster. So we get another dendrogram here. Okay? So it is very easy for this simple example, but then the question is, if we have larger graphs with many more nodes and many more connections, can we do it? So we need a mathematical criteria, and I'm going to tell you one mathematical criteria that is well known in the literature. So this is something called the modularity optimization. So what is modularity optimization? I'm going to go through the math so that you can see the limitation of this, and then I will motivate our formulation. Okay, so what is this? Well, this is the score is defined by this formula. K here corresponds to the total degree. So for this example, the total degree is 2. So because node 1 has degree 1 degree, and then node 2 has degree 1. So altogether 2. Kj corresponds to the degree of particular node. For example, K1 has degree 1, and then K2 has degree 1, and K3 has degree 0. Okay, so that's quite obvious. Okay. Now, what is interesting is this term. This term is calculating the difference of these two terms. The first one is basically the fraction of edges, fraction of degree that is between two nodes. For example, if you look at node 1 and 2, then it will be 1 over 4. So it is also ordered. So you can also look from with I equal to 2 and then j equal to 1, and it will be 1/4 as well. And then you have a subtraction term. So this is the penalization. So what is Ki and Kj? This is the degree of the node. So it is roughly, if you are randomly putting the edges and respecting the degree of the nodes, then this would be roughly the fraction of edges that will be formed between node I and node j. Okay, so we are talking about a random generation of the graph. So we want to look at, so this Qij will be large if there are more edges between two nodes, then it will be formed by randomly dropping the edges. Okay. Now, the most interesting term is this delta function. It's the direct delta function. It is equal to 1 if the cluster label for I and j are the same, and it is 0 otherwise. So for this example, consider this clustering assignment. Then only these 4 terms of this Q matrix. So here I put all the Qij into a matrix, and then only these highlighted terms will matter in the sum. Okay, so diagonal will always be in the sum because Ci is always the same as Ci. But then in this case, because we have a cluster 1, 2 here, then the term when I is equal to 1 and j equal to 2 is also affecting the sum. So if you calculate the sum here, the score will be precisely 0. So the modularity of this cluster assignment is equal to 0. So now how do we find the appropriate cluster for a graph? Well, we will basically go through all possible assignment of the cluster and then calculate their score and then find the one that has the highest score. So we already calculated the score for this one. What about the scores for this clustering assignment? Well, it corresponds to summing up the highlighted term here, and you can see this is minus half. What about this one? It is also minus half. And what about this one? Also minus half. You can see that the score is kind of lower compared to the first one because it's not identifying the correct clustering solution. So that seems to make sense. Now, let's continue. Now, what about this cluster? So this is the trivial cluster containing all the nodes. And what is the score? Well, you have to just sum up every term, and you can see the sum is 0. Now, the algorithm seems to be successful. We have 2 clusters. The one that is connecting 1 and 2, and then the other one that connects everything. And what's wrong with this? What is wrong is it gives the same modularity score for both this clustering assignment and also this one. But we know that this one and 2 form a stronger community. But then the modularity source does not distinguish the two. They are both equal. So this is a failure. There are actually many more issues of modularity optimization, and it doesn't just affect the simple example I show you, it also affects larger graph. So there's something called the resolution limit of modularity score. So basically what it means is modularity optimization tends to return larger cluster, larger communities than desired. So to give an example, consider this ring of cliques. So you would think that the community, the strong communities, would be just the cliques, right? Now what would happen if you run the modularity optimization? Turns out you get this pairing of cliques, okay? But the solution is not unique because you can also pair this with that instead, okay? So it is returning clusters that are larger than desired. Another problem with modularity score is there seems to be no direct extension of the score to higher order network models. So for example, hypergraph. How do you extend the formula to hypergraph? It is not clear, okay? But then high order dependency are often found in real-world networks. So the question is, how do you apply the solution to real-world networks? Perhaps the more important problem is the problem of modularity optimization is anti-hard. That's making things very difficult to, not just to compute for large network, but also difficult to analyze because you don't know, you don't have a unique solution and you cannot have a very good closed-form formula for solving it, for the solution. And actually this problem is affecting also many well-known clustering algorithms. For example, the special clustering algorithm that make use of graph conductance, infomap that use the map equation, and then size constraint, density subgraph problem, and also the web communities. All of these are anti-hard problems. Okay, so right at the formulation. So making things very difficult to analyze. So when things goes wrong, it is hard to know why it goes wrong, and it's hard to find a fix. Okay. So what do we want? So this is probably more important than the solution. So what do we want? We want basically a framework that is analyzable, so an analytical framework, but then at the same time it should have some desired properties. One of them is it should be interpretable in some domain of interest, so it connects to the real-world networks. Second one is it should be general beyond graph, so the concept should apply to real-world networks that has high-order dependency. Finally, we want polynomial time solvability right at the formulation, so not after approximation. So this makes the framework analyzable. Okay, so these are the three fundamental properties that we want to look for. And I'm going to now introduce a problem formulation that addresses all of these. Okay. So this is the game theoretic framework that I'm going to talk about. So first I will introduce some basic concepts of game. So what is a cooperative game? It starts with basically just two mathematical constructs. One is the set of players, V, which is a finite set. And then another one is the set function, G. G corresponds to the value of the coalition C. So if players in C join together, they produce something, then the value of that production, the product is G of C. Okay? Let's give an example. So this is an example involving 3 players, 1, 2, 3. And then I'm going to define the gain or the value of the coalition using a graph. So basically, it corresponds to the internal connections, internal edges of the set C. So if you look at the set C to be 1, 2, then there's one edge within this set. So G of 1, 2 would be equal to 1. Similarly, G of 1, 2, 3 is also 1 because it has one edge within 1, 2, 3. All the other subsets, G will be equal to 0. Okay? We don't just look at cooperative game. We look at a special type of cooperative game called the convex game. So why do we do that? So let me first explain what is convex game. So convex game means the function G has to be supermodular. And supermodular means this equation. So this equation may be a little bit unintuitive, but there is an equivalent statement that is more intuitive. So this is the equivalent statement, and I'm going to explain it using an example. So we have basically a set B, which is a subset of set C, and there's a node I that is outside the set C. Okay? Then we ask on the left-hand side, what is the marginal additional gain in the product when you add user I to B? So this is what happens if B produce, and then this is what happens when B together with I produce. So this is the marginal additional gain. So this is 1 for this graph. On the right-hand side, we have a larger set C, and we ask the same question. What is the marginal additional gain in the production when you add I to C? And this inequality try to require that you gain more if you add to a larger set. If you add a user to a larger set C, then you gain more. So in Chinese, what is this? This is just 轉機就蝕力啦. So basically, if you join force, then you get something better. Okay, so it's very intuitive. Now, what is we have a gain. So what? Okay. So once people generate values, then they can get back the money from what they produce. So this is called the return vector. So in particular, we are interested in looking at the grand coalition. That is when it is favorable for everyone to join force to produce something. So this grand coalition means there exists a return vector that is stable. So what do we mean by stable? First of all, the total return to all the players. So our I corresponds to the return to player I. The total return is upper bounded by the amount they can generate. Okay, that makes sense. What about the second inequality? It says that for every subset C, the sum of the returns has to be at least G of C. But what does that mean? Well, if this inequality is violated, then the subset C will break apart from the ground coalition and form their smaller coalition and then produce, because they can generate this much gain. But then if your payment is not at least that much, then they will break away. Okay, find a better way to earn money. Okay? So we define the core to be the set of all return vector that satisfy this inequality. So exactly. So let me use a picture example to illustrate the idea. So basically for this graph here, we have an inequality. The first inequality corresponds to this hyperplane. So the sum of the rate return has to be 1, upper bounded by 1. And then for the second inequality, the important one to look at is R1 plus R2. It has to be at least 1. So basically, the core corresponds to this line here. So only one line. Okay. Now, the usual problem for cooperative game is the following. It first asks, is the core non-empty? So is there a feasible return vector that allows everyone to join force and work together? So this is quite a simple question. Turns out that for convex game, the core is always non-empty. So it doesn't really, it's not interesting to answer this question for our problem. Now, if it is not empty, then there are some quantities that people are interested to compute. So for example, the value of least core, cost of stability, and coalition structure. So these are some quantity I'm not going to go into detail. But suppose because we consider convex game, so the core must be non-empty. So another interesting question is, what is a fair return? Okay. In particular, there are three notions that is very well known: Shipley value, nucleolus, and egalitarian solution. And for this example, what do you think is the fair payment? Should be this point, right? This point is kind of in the middle, and it returns 0.5 to user 1, 0.5 to user 2, which is quite fair, because when they join force, they can produce 1 unit. It gives 0 to user 3 but it doesn't have any production. Okay, so he deserves 0. Okay, exactly. Now, our goal, however, is not about Shipley value. It's not about fair payment. We are trying to find strong communities. So, in particular, we want to come up with such a dendrogram. So we want to compute this dendrogram, and the two points here correspond to the two important clusters. Can we identify them? So this is the goal. Okay. So to formulate our problem, what we are trying to do is we want to find a set of strong communities at some threshold alpha. So alpha is the similarity that we are looking at. And what it is defined is they are subsets of V with at least one element in it. And sigma of C has to be larger than alpha. Sigma of C, I'm going to define later, and it corresponds to similarity or strength of measures of strength for the subset C. So this is just trying to find all the set that has strictly larger strength than alpha. But then I have one more term, maximal. So this corresponds to inclusion-wise maximal. So why do I need this term? Because if I don't have this term, there will be too many solutions, and then the problem becomes not polynomial time solvable. Okay, so I need to impose this term and to make things simple. Okay. Now a simple guess is maybe I just define sigma C to be G of C. Is that okay? Well, that's not okay because G of 1, 2, 3, so this entire cluster is equal to 1. And then G of 1, 2 is also equal to 1. So they are the same. So you cannot distinguish the strength of the two communities. So that's back to the earlier problem we are looking at when we had the modularity score optimization. Okay. So what we do is we define the strength in a careful manner. And this formula is the mini-maxi-min formulation. So it might look a bit complicated, so let me explain it using the example here. Okay? So again, what we are trying to look at first is to, let's say, try to find the strength of the entire set of nodes. So to do that, first we try to minimize over some subset B. So let's consider B to be here. Now what we need to do next is to try to find an optimal return payment for the core of that is in the core. So what is the best return payment that minimizes RI, the return to user in B? So I'm trying to maximize the return to user in B. So the best payment is this extreme point. So I put all the payment to user 2. Okay. So the solution here for when B is equal to 2 is 1. Okay. Are there other choices of B that is small that give you a smaller value? Well, if you shift B to node 1, then you want to maximize the payment to user 1. To do that, you will shift to this point at the core and give all the payment to user 1. And then end up the value is still 1. But what about if you put B to user 3? Now can you shift the payment such that user 3 obtain a value that is larger than 0? Well, no. You can't go in the R3 axis. So if you look at the minimum, then indeed the strength is equal to 0. Okay. Now, if you consider the C to be 1, 2, you can do the same optimization, and you get, if B is equal to 2, then you are trying to push all the payment to user 2, you get a value of 1. And similarly, if you choose B to be 1, then you will push all the value to user 1, and the value is, I think, 1. So at the end, the sigma of 1, 2 is equal to 1. So this is precisely what we want. So it tells us that the strength of user 1 and 2 is larger. We call this the community support, because we are trying to give as much support we can give to users in B. So basically give all the payment to B. And therefore, this is not a fair payment. This is going to the extreme. So we are just helping members who are in need. Okay. So as I have said, we consider complex game. So the quantity about in the case when core is empty, is not relevant. And also, we are not looking at fair payment. Indeed, our measure is not fair. Okay. So there is actually a simpler example expression than the maxi-mini-max, actually mini-maxi-min expression, and this is the one. And we can also rewrite it in this form. Okay, so this is the solution, and you can check that indeed it coincides with the quantity we just computed. So I'm not going to go through this, but then you can see that this is a only one minimization only. It only concerning the subset B. Okay, so here is our formulation. So our formulation is to find the set of cluster for threshold alpha, where alpha can be any real number, and then this set of cluster correspond to subsets that has strength that is larger than alpha, and the strength is defined as follows. Okay, so can we do that? So we call our goal. So our goal at the beginning, before we formulate the problem, we want it to be general beyond graph. Well, yes, it's quite general because G is any supermodular function, and I told you how to also reduce it to graph. Well, it is interpretable in some domain, yes. It is interpretable in cooperative game as, so the strength is community support. Now, what about polynomial time solvability? Do we have polynomial time solvability? Well, this is a maximization over all subsets, so they are exponentially many subsets. Right? This is also a minimization over a subset of B, so there are also exponentially many subsets. So do we have polynomial time solution? So I'm going to explain the promising result. Indeed, we have polynomial time solution, and it's based on the submodular or supermodular function G. Okay? So the first result is that the solution can be represented by a dendrogram, by a tree. So what is the benefit of representing things by a tree? Because there's only a linear number of nodes in a tree, so it only requires linear storage. Okay, but what about the computation? Well, the computation can also be done in polynomial time. So for the first result, the proof is relying on this lemma. This lemma is quite elegant, but then let me explain it using the example we have. So suppose, actually not example, but consider a particular proof idea. So suppose I have one cluster C1 that is has a strength larger than alpha, so it's a possible candidate for C alpha. And then C2 is also a possible candidate. Then what this lemma is trying to say is that this sigma of the union of C1 and C2 is at least the minimum of each individual sigma. So this sigma is at least alpha. That means that you will not have crossing communities. If you have two communities that are crossing, then the union should be the maximal, inclusive maximal set. Therefore, you don't have crossing. So that means it reduces a lot of many candidates. For the second theorem, to show it is polynomially computable is difficult, and I will not go into it, but then it relies on a result a long time ago by Predictive, that is the principal sequence. Okay. Now the next thing is specializing the problem to graph. Indeed, we not just consider graph, but also directed graph. And for directed graph, we don't just look at the internal connections, but we also see the external connections, so the incoming links. So the in-cut is also important. So we will use a parameter beta to trade off between the internal versus the external connections. Okay? And again, a result is that this definition of G for directed graph, weighted directed graph, turns out to be supermodular. So we can talk about it as a convex game. Therefore, our framework, all the result above applies. But then not just that, first of all, we can represent it by a dendrogram, but then indeed this dendrogram can be computed more efficiently using V-square maximal computations. So when we look at graph, we can apply faster method. Okay. And in particular, if you look at the case when beta is equal to 0, that is when the in-cut is effective, but then the intensity is not effective, then we have a result saying that every node inside a community have more connections with the nodes inside the community than connections from outside the community. For example, node 2 here has one connection with another node 1 in a community, but then it receives no connections from outside. So we are talking about incoming links. So there's 0 incoming link to user 2. Okay, so this match our goal, that is identify more internal links than incoming links. Okay. So I will skip this example for the interest of time. But then I know that the slides will be posted, so at the end you can check the calculation. So, we in addition to the theoretical result, we also have experimental result. So these are the comparisons with methods called clustering that find web communities. So this is the proposed method in the past to find web communities. However, if you look at what it finds, it actually finds the peripheral of the web. It doesn't identify the web center because this is actually an approximate algorithm. So our method actually can find the web center. So this is a synthetic network. But then for real-world network, we also have promising results. So this is a result on this data set. And our problem is to find densiest subgraph. So subgraph that are dense, that has many edges. So with beta equal to 1, then we are able to find many more dense subgraph compared to the existing method. Now finally, we also compare with many well-known clustering algorithms on graph, workshop, info map, and fast 3D and all this. And so this is the plot of the strength, actually the community support versus the size of the community you find. And the black one are what we find. And you can see that what existing algorithm fails to find is they fail to find a large cluster that has that are strong. So they are able to find small communities that are strong, but then they are not able to find large communities that are strong. Okay. So in conclusion, we have proposed a framework. We have studied a framework that is interpretable, polynomial time solvable, and also general. We are also looking into building strong communities, not just detecting them. We also want to improve the computation so that it is not V-squared maximal, but something faster. And then we also have alternative formulations using other notions of in-game theory. And there's no publication available for you to look at the details. So this talk is indeed the only reference you can get. And we also have some code already implemented. So if you want, you can value engineer and understand how the algorithm works. So that's all my talk. That's all. Thank you very much.
Yeah, we have time for questions. So can I ask a question? So at your last slide, you mentioned that you used a greedy algorithm. So is that possible for making this kind of algorithm to be parallel?
Parallelizable, yes. Actually, we already have done one parallelization step. So it is parallelizable, but it's still not fast enough. So right now, the algorithm does not work on a graph that is too large. It also depends on the Maxwell algorithm implementation. So we also do not haven't optimized the Maxwell computation yet. Yeah.
Thank you. If we don't have more questions, let's thank others, our speaker again.